Physics, the study of matter, energy, and the fundamental forces of the universe, has a rich history filled with fascinating discoveries and brilliant minds. One interesting fact is that the word physics comes from the Greek word physis, which means nature. The ancient Greeks were among the first to ponder the nature of the world around them, with philosophers like Thales and Pythagoras laying the groundwork for later scientific inquiry. Moving forward in time, the Renaissance and scientific revolution marked a period of great advancement in physics. Scientists like Galileo Galilei and Johannes Kepler made groundbreaking discoveries in astronomy and mechanics, challenging long-held beliefs and paving the way for the modern scientific method. In the realm of classical mechanics, Sir Isaac Newton's laws of motion and universal gravitation revolutionized our understanding of the physical world. One particularly intriguing number is the speed of light, which is approximately 299,792,458 meters per second in a vacuum, a fundamental constant in physics. As we delve into electromagnetism, the work of James Clerk Maxwell stands out. Maxwell's equations unified electricity and magnetism, leading to the prediction of electromagnetic waves and the development of modern technologies. Transitioning to the realm of quantum mechanics, Max Planck's discovery of quantized energy levels challenged classical physics and laid the foundation for a new understanding of the subatomic world. Albert Einstein's theory of relativity further reshaped our understanding of space and time, introducing the concept of space-time as a unified entity. Today, modern physics continues to push the boundaries of our knowledge, with quantum field theory seeking to reconcile quantum mechanics with the principles of special relativity. The history of physics is a testament to human curiosity, ingenuity, and the relentless pursuit of knowledge. Ancient Greece is renowned for its significant contributions to the development of science and philosophy, with key figures like Thales, Pythagoras, and Aristotle laying the foundation for future scientific inquiry. Thales, often considered the first philosopher of the Western tradition, proposed that water was the fundamental substance of the universe, marking an early attempt to explain natural phenomena through rational thought. Pythagoras, known for his theorem in geometry, also delved into the realm of cosmology, believing in the harmony and mathematical order of the cosmos. One interesting aspect of Pythagorean philosophy is the concept of the music of the spheres, which posited that celestial bodies moved in accordance with mathematical relationships, producing a celestial harmony. Moving on to the realm of astronomy, the ancient Greeks made significant strides in understanding the motion of celestial bodies. Aristarchus of Samos, for instance, proposed a heliocentric model of the solar system, with the Sun at the center and Earth and other planets orbiting around it. This revolutionary idea challenged the prevailing geocentric view and foreshadowed the heliocentric model later championed by Copernicus. An intriguing numerical fact is that the ancient Greeks were able to calculate the circumference of the Earth with remarkable accuracy. Eratosthenes, a Greek mathematician and astronomer, famously calculated the Earth's circumference by measuring the angle of the sun's rays at two different locations and using simple geometry, arriving at a value very close to the modern estimate. In the realm of physics, Archimedes, known for his contributions to mathematics and engineering, made significant advancements in the understanding of buoyancy and the principles of levers and pulleys. Archimedes' principle, which states that the buoyant force on an object is equal to the weight of the fluid it displaces, remains a fundamental concept in fluid mechanics. An interesting anecdote is Archimedes' famous exclamation, "Eureka! I have found it!" when he discovered a method to determine the purity of gold using water displacement. The ancient Greeks' emphasis on observation, reason, and mathematical rigor laid the groundwork for the scientific method and shaped the course of scientific inquiry for centuries to come. The Renaissance and scientific revolution marked a pivotal period in the history of physics, characterized by a resurgence of interest in scientific inquiry and a shift towards empirical observation and experimentation. One fascinating aspect of this era was the development of new instruments and techniques that revolutionized the study of the natural world. For example, the invention of the telescope by Galileo Galilei in the early 17th century allowed for unprecedented observations of celestial bodies, leading to groundbreaking discoveries in astronomy. Galileo's observations of the moons of Jupiter and the phases of Venus provided compelling evidence for the heliocentric model of the solar system proposed by Copernicus. Another interesting development during this time was the refinement of the scientific method, with Francis Bacon advocating for systematic experimentation and induction as the basis for scientific inquiry. Bacon's emphasis on empirical evidence and the importance of falsifiability laid the groundwork for modern scientific practice. An intriguing numerical fact is that during the scientific revolution, the field of physics saw a rapid expansion in the number of scientific publications. For instance, in the 17th century alone, the number of scientific journals and publications increased significantly, reflecting the growing interest in sharing and disseminating scientific knowledge. One notable figure from this period is Johannes Kepler, whose laws of planetary motion revolutionized our understanding of the dynamics of the solar system. Kepler's laws, which describe the elliptical orbits of planets around the Sun, provided a mathematical framework that laid the foundation for Newton's later work on universal gravitation. In the realm of optics, the work of Sir Isaac Newton on the nature of light and color was particularly groundbreaking. Newton's experiments with prisms demonstrated that white light is composed of a spectrum of colors, leading to the development of the theory of color and the understanding of light as a wave phenomenon. An interesting detail is that Newton's groundbreaking work on optics was published in his seminal work, Optics, which presented his experiments and theories on light and color. The Renaissance and scientific revolution not only transformed our understanding of the physical world, but also laid the foundation for the modern scientific method and the interdisciplinary nature of contemporary physics. Classical mechanics, as formulated by Sir Isaac Newton, revolutionized our understanding of the physical world and laid the foundation for modern physics. One interesting detail is that Newton's laws of motion, particularly his second law, force equals mass times acceleration, provided a quantitative framework for describing the relationship between force, mass, and acceleration. This law is fundamental to classical mechanics and is still widely used in physics and engineering today. Another intriguing aspect of Newton's work is his law of universal gravitation, which states that every particle in the universe attracts every other particle with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. This law not only explained the motion of celestial bodies, but also provided a unifying principle that applied to objects on Earth as well. An interesting numerical fact is that Newton's Principia Mathematica, in which he laid out his laws of motion and universal gravitation, is considered one of the most important scientific works ever published. The Principia revolutionized the field of physics and set the standard for scientific inquiry for centuries to come. In addition to his work in mechanics and gravitation, Newton also made significant contributions to the field of optics. His experiments with prisms demonstrated that white light is composed of a spectrum of colors, leading to the development of the theory of color and the understanding of light as a wave phenomenon. Newton's groundbreaking work in optics further solidified his reputation as one of the greatest scientists in history. The legacy of classical mechanics and Newton's contributions to physics continue to shape our understanding of the physical world and inspire future generations of scientists and researchers. In the realm of electromagnetism, one of the most significant figures in the history of physics is James Clerk Maxwell. Maxwell's equations, a set of 4 fundamental equations that describe the behavior of electric and magnetic fields, revolutionized our understanding of electromagnetism and laid the foundation for modern physics. An interesting detail is that Maxwell's equations predicted the existence of electromagnetic waves, leading to the realization that light is an electromagnetic phenomenon. This unification of electricity, magnetism, and light into a single framework was a monumental achievement in the history of physics. One fascinating aspect of Maxwell's work is that he demonstrated that varying electric and magnetic fields can propagate through space as self-sustaining waves, traveling at the speed of light. This insight not only confirmed the wave nature of light, but also paved the way for the development of technologies such as radio, television, and wireless communication. An intriguing numerical fact is that the speed of light, a fundamental constant in physics, is approximately 299,792,458 meters per second in a vacuum, a value that plays a crucial role in Maxwell's equations and the theory of electromagnetism. Maxwell's contributions to the field of electromagnetism were so profound that his equations are still used today to design everything from electronic devices to telecommunications systems. The impact of Maxwell's work extends beyond the realm of physics, influencing fields as diverse as engineering, chemistry, and biology. Maxwell's groundbreaking insights into the nature of electromagnetic fields and waves continue to shape our understanding of the universe and inspire new discoveries in science and technology. Quantum mechanics, a branch of physics that deals with the behavior of particles at the smallest scales, revolutionized our understanding of the subatomic world. One of the key figures in the development of quantum mechanics is Max Planck, whose work on the quantization of energy paved the way for a new era in physics. An interesting detail is that Planck introduced the concept of quantized energy levels, proposing that energy is emitted or absorbed in discrete packets called quanta. This idea challenged classical physics and laid the foundation for the quantum theory of matter and radiation. Planck's groundbreaking work on blackbody radiation, where he derived a formula that accurately described the spectral distribution of energy emitted by a blackbody at different temperatures, provided crucial insights into the nature of energy quantization. An intriguing aspect of Planck's constant, a fundamental constant in quantum mechanics, is that its value is approximately 6.626 times 10 to the power of negative 34 joule seconds. This constant relates the energy of a photon to its frequency and plays a central role in determining the behavior of particles at the quantum level. Planck's constant is a cornerstone of quantum mechanics and underpins many of the phenomena observed in the subatomic realm. Moving beyond Planck's contributions, quantum mechanics introduced a new framework for understanding the behavior of particles, characterized by probabilistic outcomes and wave-particle duality. One fascinating aspect of quantum mechanics is the principle of superposition, which states that particles can exist in multiple states simultaneously until measured, leading to phenomena such as quantum entanglement and quantum teleportation. Another intriguing concept in quantum mechanics is Heisenberg's uncertainty principle, which posits that the more precisely the position of a particle is known, the less precisely its momentum can be determined, and vice versa. This fundamental principle sets limits on the precision with which certain pairs of properties can be simultaneously measured. An interesting numerical fact is that the speed of light, a universal constant, plays a crucial role in quantum mechanics. The speed of light in a vacuum is approximately 299,792,458 meters per second, a value that influences the behavior of particles and waves in quantum systems. Quantum mechanics has led to the development of technologies such as lasers, transistors, and MRI machines, revolutionizing fields ranging from telecommunications to medicine. The principles of quantum mechanics continue to inspire new discoveries and innovations in science and technology, shaping our understanding of the universe at the most fundamental level. Albert Einstein's theory of relativity revolutionized our understanding of space, time, and gravity, introducing a new framework for describing the universe. One interesting detail is that Einstein's theory of special relativity, published in 1905, proposed that the laws of physics are the same for all observers, regardless of their relative motion. This principle led to the famous equation E equals mc squared, which states that energy, E, is equal to mass, m, times the speed of light, c squared. An intriguing aspect of this equation is that it demonstrates the equivalence of mass and energy, revealing the profound interplay between matter and energy in the universe. In the realm of general relativity, Einstein proposed a new theory of gravity, describing it as the curvature of spacetime caused by mass and energy. This revolutionary concept led to predictions such as gravitational time dilation and the bending of light around massive objects, which were later confirmed through observations. An interesting numerical fact is that the speed of light, a fundamental constant in relativity, is approximately 299,792,458 meters per second in a vacuum, a value that plays a central role in Einstein's theories. General relativity also predicts the existence of black holes, regions of spacetime where gravity is so strong that nothing, not even light, can escape. The first image of a black hole, captured in 2019 by the Event Horizon Telescope, provided direct evidence of these enigmatic cosmic objects. Einstein's theories of relativity have had a profound impact on modern physics, influencing fields such as cosmology, astrophysics, and particle physics. The principles of relativity continue to shape our understanding of the universe, inspiring new avenues of research and exploration. Modern physics, characterized by the study of phenomena at the smallest scales and highest energies, has led to profound insights into the nature of the universe. Quantum field theory, a framework that combines quantum mechanics with special relativity, describes the behavior of particles as excitations of underlying fields. One interesting aspect of quantum field theory is the concept of virtual particles, which are temporary fluctuations in energy that arise due to the uncertainty principle. These virtual particles play a crucial role in fundamental interactions, such as the electromagnetic force. An intriguing detail is that quantum field theory predicts the existence of force-carrying particles called gauge bosons, which mediate interactions between matter particles. For example, the photon is the gauge boson responsible for the electromagnetic force, while the W and Z bosons mediate the weak nuclear force. In the realm of particle physics, the Standard Model is a successful theory that describes the electromagnetic, weak, and strong nuclear forces, as well as the known elementary particles. An interesting numerical fact is that the Higgs boson, a fundamental particle predicted by the Standard Model, was discovered in 2012 at the Large Hadron Collider. The discovery of the Higgs boson confirmed the mechanism by which particles acquire mass and provided crucial evidence for the validity of the Standard Model. Quantum field theory has also led to the development of quantum field theories of gravity, such as string theory and loop quantum gravity, which aim to unify gravity with the other fundamental forces. These theories offer new perspectives on the nature of space-time and the fundamental structure of the universe, challenging our understanding of physics at the most fundamental level. One key personality in physics is Marie Curie, a pioneering scientist known for her groundbreaking research on radioactivity. Curie was the first woman to win a Nobel Prize and remains the only person to have won Nobel Prizes in 2 different scientific fields. Another notable figure is Richard Feynman, a brilliant physicist known for his work in quantum mechanics and quantum electrodynamics. Feynman was a charismatic teacher and communicator, famous for his lectures and books on physics. A fascinating fact is that Feynman was also an accomplished bongo player and artist. Moving on to modern physics, Stephen Hawking made significant contributions to our understanding of black holes and the nature of the universe. Hawking's book, A Brief History of Time, became a bestseller, bringing complex scientific concepts to a wider audience. Throughout the history of physics, we have encountered fascinating personalities and groundbreaking discoveries that have shaped our understanding of the universe. From Marie Curie's pioneering work on radioactivity to Richard Feynman's contributions to quantum mechanics, each scientist has left a lasting impact on the field. An interesting fact is that the speed of light, a fundamental constant in physics, plays a crucial role in many theories and equations. Another intriguing detail is that the discovery of the Higgs boson in 2012 provided experimental evidence for the mechanism of particle mass generation. As we reflect on the key personalities and discoveries in physics, we are reminded of the curiosity, creativity, and perseverance that drive scientific progress. The history of physics is a testament to the power of human intellect and the quest for knowledge.